Hello everyone and welcome to another webinar from Würth Elektronik. I'm very happy to welcome all of you. My name is Markus Eberle and I will moderate this webinar today, but way more important is the man next to me, Timur. Hello.
Thank you, Markus. Thank you, Markus.
Of course, you're welcome. The topic of today is decreasing the BOM and improving common mode noise reduction. I'm very curious. It sounds very good, this title. So I'm very curious what's the content of it. And yeah, so that's enough from my side. Have fun with the webinar and yeah, enjoy it. Timur, stage is yours.
Thank you. So, as Markus already said, decreasing the BOM and improving common mode noise reduction. So the whole webinar will be somehow clustered in 4 different parts. First part is that I will show you a little bit about the EMI basics. What is a Y-capacitor, how he is acting. Second, we will go for the realized layouts we have for the power modules and see how the different layouts perform EMI-wise. Third part will be that we look how a layout for digital isolators can be optimized with stitching capacitor layout. And last but not least, we will show you a little bit about the additional tools we have from Würth Elektronik to help you to come to a very good layout, very, very easy. So, first, EMI basics. Here you can see the schematic here of an isolated power module. You have got here the power supply and here you have got the load resistor. For further, it is very important to understand the difference between differential mode and common mode disturbances. First, the differential mode here, as you can see, the green arrows, they go in the power module and they come out the power module from the input and let's say circulate here over the power supply. That means they have got the same direction as the switching current. The common mode noise is a little bit different here. Here you see it goes in, and the return path here is over the parasitic capacitance to earth, back here, so that the whole circuit is closed here. What is a parasitic capacitance? If you, let's say, take the power module, as you saw on an evaluation board, you put the input cables, you put the output cables, the load and everything, and make then, let's say, a reference surface out of it, then you have something like here, 2 parallel planes that form a capacitor. And secondly, if you have one conductor here with a potential that has a different potential here to the plane, then you will also have here a parasitic capacitance that is formed here. To have a test setup that is, let's say, not interfering with the device under test, we have here something that we say we have got here our device under test. This is then the evaluation board with the power module or the digital isolator. We have got the input cables. We have got our listen here, the line impedance stabilization network, so that we can see here over the EMI receiver how the EMI performance is. We have got here the power supply and we have got here the load. And here we have then the parasitic capacitance to the ground reference. This test setup is defined by the CISPR 1621 and is suitable for us so that we can, let's say, judge the different layouts, how the EMI performance is. The most elegant way would be to pass the EMI test in terms of common mode noise would be that the current, that the noise current is not reaching the listen, so that we do not see anything in the graph. Normally, the pass here, pass 2, from the common mode noise would be that it goes out of the power module and through the ground reference here, the circuit is closed. The best would be if we somehow can force the common mode current that he goes through the power module, goes out, and then, let's say, arc here around the power module and circulates here. This is then the blue one here. This path 1 would be if we make a branch here. This branch here, as we show it here with that, is then a capacitor, our Y-capacitor we are talking today here in the webinar, and how we can implement it. But how can we calculate these capacitor? To go for an equation, we have to understand that the whole circuit can be drawn like this, that we say we have got here our line impedance stabilization network, we have got here the power module, and we have got here our load resistor. Normally, as already told, it would go like this here, but what we want to have is, we want to have here a branch circuit so that it circulates around the power module and within the power module. If we redraw this, then this would be here the simple circuit on which we can now take our Kirchhoff's equations and try to find a simple equation to go for the value of the Y capacitor that is shown here. For this, we take this circuit again. First, we will calculate the voltage V1 here. That is the voltage drop over the listen without this branch circuit, without the Y capacitor. Secondly, we will calculate the voltage drop V2. This is then the voltage drop with our branch circuit with the Y capacitor. And if we then take these two equations, put them in the normal damping equation, then we will get something like this here. This we can use then to calculate, based on the damping we want to have, the capacitance value, or we put in here the capacitance value and get then the damping in dBs we want to achieve. Last but not least, we need the equation and also the understanding about what is a stitching capacitors. There are a lot of, let's say, ways to make a stitching capacitors. We will go here for a gap overlapping stitching. That means the capacitance is formed by the overlapping area you have between two different potentials, two different layers here. As you can see, this is the width and this here is the length. So this whole area forms then between the green, white and the gray one here, the capacitance value. Now we know which equations, which basic knowledge we need to go for a stitching capacitor. We have to think a little bit about which measurements, which versions of layouts would make sense here. We have chosen here 4 different layouts for the power modules based on an 80 by 80 millimeters PCB size. First, we will go for a 2-layer without a Y capacitor. I put this without here a little bit different because it would better to say without intentionally wanted Y capacitor. But I come on to this point later. Second, 2 layers where we have the most capacitance we can create by remaining the distances, the creepage distances from the power module. The third layout would be a 4-layer design where we have a separated ground and top and bottom layer. And the 4th layout is the layout where we try to maximize the capacitance as much as possible, what we can do for a 4-layer design. More than 4 layers we will not go for because 2 and 4 layers are, let's say, common practice. Yeah, you can go for a 6 or an 8 or a 10-layer layout, but for a power module this is not necessary, and this is why we skip this and only go for the 2 and the 4-layer layout. So now we will go for the realized designs. But what is missing? The power module we have to take here as the power module so that we have got here something that can produce this noise. We take here our new FIMM LGA 7 power module that is very, very tiny, highly integrated. And here we have only a typical parasitic coupling capacitance of 8 picofarad. To be, let's say, safe in terms of are we really covering the common mode noise, we put here an input filter and also an output capacitor so that we are sure that we mostly go for the common mode noise and see here for the Y capacitor the effects on different Y capacitor values. So layout version 1. Layout version 1 is a simple layout. We have got here on the top layer, we have got here the secondary ground, and on the bottom layer we have fully the primary ground. So that means between secondary ground, primary ground, as you can see in the schematic structure, there we will have a capacitor. This capacitor is already 14 picofarads. But as you can see, here there was no intention to form a capacitor, but as we see that also a simple 2-layer layout forms a capacitor, that gives us the first hint how we can make it. Second layout, we go for primary ground on the top layer, and secondary ground we go on the bottom layer. Here we have tried to maximize the overlapping area on a 2-layer design. And as you can see here in the schematic structure, the capacitor is formed between primary ground and secondary ground. Here we will go for a 130 picofarads capacitor. But what about the EMI performance? Let's check this. The EMI performance of a 2-layer design without any intentionally wanted Y capacitor looks like this. Please remember we are here at the 80 by 80 millimeters PCB with a power module on it and no additional common mode suppression. Here you can see that we are, let's say, nearly crossing a little bit the class B limit here, but a class A would be here very, very sufficient. If we now compare the design without intentionally wanted capacitor to the 2-layer with the integrated 130 picofarads capacitor, then you can see that we have here an average value about 10. If we take it here and calculate it, we have 12 dB attenuation here for the 130 picofarads capacitor. Would mean for me the equation we have shown is more than sufficient to go for a first starting value. Next, if we now take the design we had without this intentionally wanted Y capacitor and add a discrete 100 picofarads capacitor and make here a comparison to the two layer with 130 picofarads capacitor, then we will see there is nearly no difference. Here at the end we have a little bit here, but at the average value, if we go and say, okay, how many margin we have to cross here the border of the class B, then there is nearly no difference. Would mean it is the Y capacitor itself, and as you can see also it can be placed as a discrete one or as an integrated one. So let's go for the 4-layer version. For the 4-layer version, we have realized one design here with 920 picofarads. Here we have on the top layer the primary ground, the secondary ground, and on the bottom layer, as you can see, the same primary ground and secondary ground, and layer 1 and layer 2 are completely with secondary ground and primary ground. That means here we will have more than one capacitor. Here we have one capacitor between secondary ground and primary ground. The next one is between primary ground and secondary ground. And the last one is between secondary ground and primary ground. This is why we then have here 920 picofarads. Please remember, we're talking here about 80 by 80 millimeters only, so not much size. If we then check the EMI performance, then you will see that the 4-layer design with integrated 920 picofarads has at around 28 dB attenuation based on our design without any intentionally wanted Y capacitor. If we then do the same exercise as we have it for the 100 and 130 picofarads version, then you can see if we place on the 2-layer design a 1000 picofarads discrete capacitor, we have nearly the same shape and have nearly the same values. Yes, of course, we have here some spikes, as you can see, where we have here a little bit more damping, but if we go to the overall, then you can see there is not much difference here. That means also a 2-layer design with 100 picofarads discrete is somehow equal to a 4-layer design with a 920 picofarads integrated version. The last version I will show you now, there we have tried to optimize the capacitance as much as possible. Means we modified here the primary, the top layer and the bottom layer as we did it for the 2-layer with the 130 picofarads, that we have got here the complete top layer as secondary ground, the complete bottom layer we have got here as primary ground, and layer 1 and layer 2 stayed the same. Here we have the complete area used for the potential. Here we have then also 3 different capacitors. The first one is between secondary ground and primary ground, so from here to here. Then from primary ground to secondary ground, from layer 1 to layer 2, and then we have also from layer 2 to bottom layer the third one. That means from secondary ground to primary ground. This is now the maximized version. This is the most you can get from a 4-layer design for 80 by 80 millimeters. Here we are talking about 1,400 picofarads as an integrated capacitance. If we now compare the 4-layer design with 1,400 picofarads capacitor with the 4-layer with 920 picofarads integrated capacitor, then you can see, yes, we have here a little bit more damping, here a little bit less, but in the average, I would say it is nearly the same. So between 1,400 picofarads and 920 picofarads, there is not much difference. So if we go now for our evaluation board, then you can see we started here with nearly no capacitance. Yeah, we have got 14 picofarads, but not intentionally wanted. Then we take this design we add a 100 picofarad discrete version. Then we see, okay, we have a little bit of margin here, but this is not enough for us. And then we jump to 470 picofarads and can see that between here and here we get a little bit of 20 dBs. That means we have here enough margin so that we can work with this. That means for the evaluation board, as an evaluation board where you can play with, we put a 2-layer design with an external 470 picofarads Y capacitor to show here that we can easily go for class B here. Now let us summarize what we have seen now in this chapter about the EMI performance of the different layouts. So our first version was the 2-layer design where we have a Y capacitor but not intrinsically wanted, where we have got 14 picofarads. Here, if we go for an EMI judgment, I would say this was not enough. Second layout, we had a 2-layer design with an integrated capacitor of 130 picofarads. This is somehow judged as a good EMI performance. The third one, we have got this 4-layer design where we have got separate primary ground area on top and bottom layer. There we go for nearly 920 picofarads. This is much better than the one with 130 picofarads. The last one, the 4th layout we have here is with 1,400 picofarads, but as we saw, there's nearly no difference for the EMI behavior between 3 and 4. Now, normally the question come up, yeah, but when should I use a stitching capacitor? When should I use a discrete one? Why should I use it? Let's check the advantages and the disadvantages of a Y capacitor and a discrete capacitor. First of all, as it is already in the title, decreasing the BOM. The BOM, the overall, is reduced because this part, Y capacitor, is integrated, so you don't need it to place, you do not have to buy it, you do not have to store it, or the other logistics. This is why we say the BOM is reduced. But as a disadvantage, we could go for and say, yeah, but if I start the layout, from the first day I make the layout, I have to think about that there has to be a Y capacitor integrated. we also can say here no additional cost. That means if we have more designs or a bigger design where you have more Y-capacitors, then it can take into account that as the BOM is reducing, the costs will also reduce. As a disadvantage, somehow it is, if I want to, let's say, optimize more, then it is not possible if it is an integrated version, because then this is automatically leading to a new layout. If the Y capacitor would be placed discrete, you can take it out, take the next one from us and make your tests. For me personally, one of the biggest advantages for a stitching capacitor is this point here. With a Y capacitor that is integrated, you can easily generate a basic isolation, you can generate a reinforced isolation, and to go for a reinforced isolation with a discrete capacitor is more difficult, because then it's getting bigger, this capacitor, because then you are bridging the primary from the secondary side. You make the bridge, and therefore also the safety aspect has to be taken account. If this capacitor is integrated in the layout, then it is more easy to go for this. Let's take a look. Special for this last point, insulation types such as reinforced can be realized easily for our digital isolators, because here we have a reinforced and a basic isolation, and we saw that it also works here pretty well. So the realized designs are, we go for a 80 by 80 millimeters PCB and generate 600 picofarads as integrated capacitor, where we have got here layer 1, layer 2 and the bottom layer, and that is mainly taken into account for the capacitance. As you can see here, we have got two of them. From between primary ground and secondary ground, we have got a capacitor, and between secondary ground and primary ground on the bottom layer, we have got the second one. That, as mentioned, leads to 600 picofarads. If we check the EMI performance, we also check here not only the conducted, we also check the radiated, because we are having here a digital isolator that is transferring signals with 150 megabits. And there you can see that with the 600 picofarads, we are far away from any limit. That means for class A, we are more than enough, and also for the radiated ones, you can see we are very far from the limits here. Normally, now the question would come, yeah, but you're only going for, let's say, evaluation boards. There's all standardized. You have got 80 by 80 millimeters. This is more as a laboratory experiment. Yes, and therefore, we also created a potential-free measurement reference design, where we see here it is a more complex application. Here you go for the voltage measurement, so you measure a battery somehow in a stationary battery compartment. Here you go for the measurement, then the signal is going through the twisted pair cable, and is going then here through and out to the operator. Here we have placed our digital isolators here, and also here our power module here and here. And there you can see that this is a more complex application, but also in this more complex application, you can go easily for a 4-layer design with 1000 picofarads integrated capacitor. As you can see, here we check the receiver, that if you have got here the ground primary, we have got here the bottom layer and the internal layer 2. The top layer is not, let's say, does not make much sense to show here, because the ones that make the more capacitance are these 3 layers here. And as you can see, we have here between ground and ground primary side, we have got the first capacitance, and between ground primary side and ground here, so our bottom layer, you have got the second one. The second one here is taking more into account because here we have got the less difference, so we have got the more capacitance. Let us check also here the EMI performance. If we go here for the 4-layer design with coupling capacitance, then you can see that we have here a lot of margin to the values here where we would cross the class B. But remember, this is not now an evaluation board, this is a more complex application, and you can see it is easily manageable to go for such a design with 1000 picofarads. If we then also compare, because we also did this exercise, that we make the design of the reference design as a 2-layer one, then you can see here a 2-layer design without any filtering against the one where we have got this 4-layer design with this 1 nanofarad capacitance. Then you can see how the levels drop here. So there is enough margin for class B. But to be honest, to make a 4-layer design where you have, let's say, all the capacitance values you need thought about, where you have designed it with all these wires and everything, this is something where you need some experience. This is nothing you can go for a rookie. So here, Würth Elektronik did something that's called design examples. That means we provide here in our data sheet or in the online catalog layouts you can take, you can follow, and then if you do the layouts like we show it here, or if you make the download for the power module and go for the design example, then it is easily manageable that you put it in your Altium design and have exactly the layout you need to pass the EMI, and also with the right stitching capacitor configuration. So I hope you enjoyed what I told you, and I try to give you a little bit more insight. If you have any further question, please don't hesitate to go for our service and support. We have our support hotline, power modules, at we-online.de, where we have got some colleagues that answer your questions, or please contact our 4 BDMs if you have any additional questions. Thank you. And now I'm here for your questions. I hope there are some.
Yeah. So first of all, Timur, thank you very much.
You're welcome.
So there are some questions, but you also have now the possibility to ask us all your questions. I also uploaded now the handout, so you should be able to download it. And Yeah, so then we have a look at the questions, and we will start with this one. Yeah, why can you make a capacitor from different PCB layers?
Easy question. Every potential that has a difference to another potential, like I showed it with this with these two planes on the one of the first slides. If you have got two potentials with different, if you have got two planes with two different potentials and they have got a difference, then there's automatically a parasitic capacitance. And this parasitic capacitance we are using for the stitching capacitor.
Okay, thank you very much. Then next question. What types of insulation can be produced with a stitching capacitor?
With a stitching capacitor, you can get for a functional isolation, a basic isolation, or reinforced isolation. This is pretty easy, manageable.
Okay, so the next question I see here is this one. Why is a discrete Y-capacitor used in the EVB or of the isolated power module FIM?
We did this here because the evaluation board purpose is to evaluate. That means we want the customer, the user, to play here and to get more experience with our power module. And this is why we said, okay, the Y capacitor has to be placed as a discrete version so that he can take it out from the 100 or 470 picofarads. He can put in a 1 nanofarad one, or he can reduce it or can do and can somehow go for the EMI performance he is targeting with his application. This is why we have it as a discrete version.
Okay. Timo, thank you very much.
Thank you, Markus.
As far as I can see, this was the last question. And yeah, I hope you enjoyed our webinar. So we are already at the end. And if there are some questions left on your side, then just contact us later via email. And yeah, we will be there and support you. So thank you very much. It was a pleasure to have you here, Timo.
Thank you, Markus. Always a pleasure for me to be here.
And yeah, have a nice time and hope we can welcome you also to our next webinar. Thank you. Bye.
Thank you. Bye.